Good afternoon, students. So I want to kind of tell you about where to go for today, and then I want to kind of go over the teacher notes for you, so that way you can make meaning of what we're talking about today, which is the Doppler effect. So we're going to be using the electromagnetic spectrum and applying this effect, which is from Doppler. So we're going to be talking about how waves, whether it be light or sound, change and they shift. So let's go ahead and begin. So where you're going to go today is you're going to go to classwork, and then you're going to click on Thursday. You're going to start off where I'm at here, which is, do you see what I hear? These are the teacher notes. And then once you have gone through this and taken your notes, which I have a star next to the items that you need to make sure are written down, they're the important parts of the lesson. Then you're going to go here to the making meaning questions, which look like this. And you're going to use your notes that are attached to this for today's assignment to answer them. So make sure you complete these, and there's not many, but these are going to be graded. So make sure that you please answer these questions. After you finish that, then what you're going to do is I have an Edpuzzle that kind of has a good video about the Doppler effect, and you'll just answer the embedded questions with it. Okay, so I'm going to start with a video because I feel like the Doppler effect is really best explained for you to visually see what I'm talking about here. So I'm going to show the video that's first. It's not the Edpuzzle, it's a different video. I'm going to show this one first, and then I'm going to talk about the teacher notes. So here we are. I'm going to go and begin.
The Doppler effect. In Shelton's words,
it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples in a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it, they're spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of those applications. So let's say you are standing in the middle of a road. That's you, and the car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The honk to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency.
At this point, just kind of put into your mind also what you probably see quite often is an ambulance or a police car whizzing by you. This is the same thing. So when it comes closer to you, you're going to hear it a lot. It's going to be a lot louder. And then as it's moving away, you're going to see it start to recede. And this is important because I'm going to be talking about how this is applied in space with light here in a moment.
A lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does that mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color.
It changes color because it's going to stretch as it gets farther away from you, just like at the sound waves. When you saw them bunching together, light stretches.
Higher frequency light waves mean bluer light, and lower frequency light waves mean a redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future.
So what he's trying to say is that this is proof, the astronomers found proof that our universe is expanding, which means it's getting bigger and bigger because objects in space are moving away from us. Good afternoon. I wanted to go through the teacher notes with you. So I'm going to start here. So waves, they transfer energy from one place to another. That's kind of what we learned from the last lesson with the doing the wave. So when the source of the energy moves, the waves also move, or what we call shift. So consider an object such as a ball making an annoying sound. When the ball is sitting on a table, the sound waves spread out in a circular pattern around the ball. You will notice that no change in the sound. The waves generated by the ball are equal distance apart. When the ball is carefully tossed to another person in the room, however, the waves will bunch up in the direction of the throw. So the distance between the sound waves in front of the object is going to be smaller. So the person catching the ball would notice that the frequency, which is the amount of waves per second, is increased because the annoying sound would have a higher tone or pitch. The person throwing the ball would notice something different because since they're going to be away from the ball is moving away from them. The waves behind that object are going to be spread further up or spaced further apart. So the distances between the waves are further apart, so the annoying sound has a lower pitch because of the frequency decreasing. So this apparent change in the wavelength or frequency when an object is moving is known as the Doppler effect. So this is why, from this picture here with the siren, this is probably the one that you can think of as the most common example because you hear sirens all the time, is that when the siren is coming towards you, it's going to be higher in pitch. You're going to hear, it's going to be really loud. And then once it passes you, and this has to go pretty fast when they're going for you to actually notice the change, but when they whiz by you and they go, they're leaving you, you're going to notice that pitch is going to get lower because it's moving away from you. So this is the Doppler effect. So it's not only for just sound, it's also going to be working for light waves as well. So light and sound is going to be wave energy. So when an object moves away, the waves are going to appear longer, which we call a red shift. And then when the objects approaching the waves appear shorter, that's what we call a blue shift. And here in a moment, I'm going to show you the electromagnetic spectrum again, and you're going to see the red and the blue in the visible light part, which that will make sense as to why red is moving away and blue is coming closer. So for sound waves, when a noisy object approaches, the pitch is going to be higher, and when a noisy object moves away, the pitch is lower, just like the siren example. So when it comes to light waves, instead of a change in pitch in the sound, we're going to see a change in the actual color, and this is due to the shift or the stretching of the wavelength. So telescopes with filters called spectroscopes scatter the starlight to produce a rainbow-like pattern called a spectrum. And the bands of colors also includes dark lines, which they're called spectral or absorption lines. So these are going to be these right here, as you can see from my mouse. So these are going to be unique to each element that make up the star itself. So the dark lines appear because the starlight is filtered by its atmosphere. Okay, so this is really, really important. So when stars or galaxies are moving away from us, the wavelengths of light appear longer and shifted towards the red end of the spectrum, and this is called a red shift. So the waves are getting stretched out. So it's going to be on the lower part of the electromagnetic spectrum. On the other hand, if it's moving towards us, like when stars or galaxies, they're moving towards us on Earth, the wavelengths of light appear shorter and shifted towards the blue end of the spectrum. And this is called a blue shift. So here's some more visuals just to kind of show you what this looks like. As you can see here at the bottom, my little thing moves. The redshift, you're going to have more red, as you can see, based with the spectral line. And then here on the blue shift, you're going to see the spectral line pointing more towards the blue or violet section of the electromagnetic spectrum. And this is just showing you from Earth versus space, the differences of a galaxy moving away from us or a galaxy moving towards us. You can see the lines shifting the color. So, okay, so distant galaxies seen through the Hubble Space Telescope. So this is something that you can't see with your own eyes. You have to have special equipment like the Hubble Space Telescope. So they study this electromagnetic radiation emitted from distant galaxies, such as the visible light, microwaves, and radio waves they give off. The redshift of this radiation gives evidence that the universe is expanding. So it's getting bigger and bigger because we're discovering more things moving away from us. Okay, and then here's the spectrum. So as you can see here, the longer waves are on the red side, and then the shorter waves are on the blue side. Okay, so one more thing before I let you go. I want to show you this video. I think it's a really cool video that kind of explains what I just talked about.
The Doppler effect. In Shelton's words,
It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
the Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it, they're spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency. And if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and the car drives past you very fast. As it does so, it honks its horn because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look at your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we see that a small change in frequency for visible light and frequency light waves means blue light, and lower frequency light waves mean redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence of the Big Bang and indeed. Okay, so just wanted to show that to you. I thought that was a great video. Okay, so after this video, I want you to answer the making meaning questions that are here. Use the notes to help you, of course. And then after that, I have in Google Classroom an Edpuzzle that I would like for you to complete. So if you have any questions, please feel free to contact me. Other than that, I hope you have a great day. Bye-bye.